Now that we know how to do math with atomic vectors in R, we can start coding up that math in our sensitivity analysis. If you recall, this analysis is motivated by wanting to look at the math of the exponential decay model, which is based in this case on first order kinetics. And we have a vector of values for time, representing time in this model, and we want to calculate the corresponding concentrations of reactant at all of those times. And to do that, we'll need a couple of parameters. We'll need a reaction coefficient, this K sub R, and we'll also need the initial concentration at the beginning of the hypothetical experiment. So I can go back to our protocol folder. I can start up RStudio using the project file. And I can bring up the script that we started, analysis.r. And here we have the rm list equals ls. That is helping us get rid of any artifacts in the global environment, make sure this code is able to run independently. And we have a times vector that we've created, an atomic numeric vector, using the sequence function with values going from 0 to 60 with an interval of half of a minute. So the next thing we need to do here is define some parameters. So I'm going to go ahead and add a comment to my code here. Define the parameters of an exponential decay model based on first order kinetics. And I need two different parameters here. I need a rate coefficient. Now I could put in K sub R here, but again, when you're writing code, sometimes it's better to use more of the word to make it easier to understand what the variable means. So I'm going to use the variable rate coefficient here. And let's start with a value of 1. And you can think about this in terms of a fraction of the reactant that is disappearing per unit time. So in this case, the dimensions of the rate coefficient is going to be per time. And in this case, because we're thinking of time in minutes, that means it's going to be per minute in terms of units. And this is a fraction of the reactant that's disappearing per minute. So we're going to lose 10% of the reactant per minute compounded continuously in this particular model. So that's our rate coefficient. We'll also need an initial concentration. I'm going to call this variable const init. And let's say we're going to start at some concentration. And you can pick the units of choice here. Let's think of this as maybe 50 milligrams per liter or 50 micrograms per liter. And then we can do our calculation. We can say we want to calculate the concentrations corresponding to the experiment times. Now let's do this calculation just a little bit at a time so we can understand what's going on. I'm going to go ahead and run the code all the way up to this line of code. I could just run the whole thing because this is just a comment. So I'm just going to hit the source button. And that's going to put things in my global environment that I can look at. So I've got a const init. That's 50. And I have a rate coefficient. That's 0.1. So these are also atomic vectors. They just have one element in them. I have a 50 and an 0.1. Now, ultimately, the math I want to do is the exponential decay. And the exponent in the exponential decay is going to be minus the rate coefficient multiplied by the time. So let's think about what's happening with math and R here. I've got the rate coefficient, a single value, but I also have time, this times, the vector of times going from 0 to 60. And this is obviously way more than just one value. So if I do a minus rate coefficient times, what's going to happen here? Well, remember R is going to recycle values. If there's one vector that's smaller than the other, it's going to recycle the value in the smaller vector as many times as it needs to match the number of values in the longer vector. So what happens when I do this math is I'm going to multiply minus 0.1, this rate coefficient, times every time in the times vector. So this is 0.1 times 0, that's 0. We've got minus 0.1 times 0.5, that's 0.05, minus 0.05. Minus 0.1 times 1 is minus 0.1. So hopefully that all makes sense. We just multiplied minus 0.1 times all of the times, and it's just recycling that 0.1 because there's only one element in that vector. So we get a vector of the same length as times out of this calculation, even though rate coefficient is just a single value. Okay, so that's our exponent. How do we do Euler's number to that exponent, or e to that value? In code, there is a function in R called exp. And exp is specifically for doing that math on a numeric vector. Now again, we can have rate coefficient times. That's what we want in the exponent. So we can type the math we just did into the exp. Now again, a lot of mathematical functions in R are automatically able to handle vectors. So we're giving this exp more than one vector, and R says, okay, you must want the exponent of each of those values. So I'm going to give you a numeric vector that's the same size as the vector you're giving the exp function, and it's going to be the exponent of each of those. So we've done our exp function. I'm going to cut and paste this so we don't have to keep typing this in. The last step is to multiply that times our initial concentration. That's the exponential decay equation. So if I do a const init times that term, again, remember this, the results of this is a vector of values, and const init is just one value. So again, it's going to recycle const init as many times as it needs to get to the number of elements in this in what comes back from this exp function. So these are the values that we're interested in, and they should start at 50 because we're starting at 0 time, and e to the 0 is 1. So we're starting at our initial concentration, and these numbers should follow an exponential decay function through to the last element corresponding to the last time in the times vector. So that's the math that we want to do, and we've gone through carefully to make sure we understand how these vectors of different lengths are resulting in the math that we're seeing. So I can say consts, because again, I like to put plural on here. This is a vector of more than one value, is going to be assigned that math. Oops, and I forgot to capture the initial concentration in that copy, so I need to do a const init here. So I have the initial concentration times the exponent of minus rate coefficient times the time. That is the exponential decay equation. If I run this whole script again, you will see that the consts have those values. So I now have a new vector that has that calculation of the exponential decay, and I have the concentrations of reactants corresponding to each of these times that I created. So we can look at these numbers and say, well, yeah, maybe that looks like an exponential decay, but it'd be really helpful to make a quick plot. We're going to learn a lot about how to make plots as part of your data products later on, but for now, just for debugging purposes, to make sure our code is working as we expect, there are quick ways to make plots directly in RStudio. And there's a higher level plot function that's simply called plot that makes it very easy to plot an x versus a y variable. So on our x-axis, we can say we want to put our times. And on our y-axis, we want to put our concentrations. And if you run plot from the console like this, without specifying any other type of device, the default device is RStudio is going to send it to this plots tab in the bottom right, or at least that's where it is by default unless you move it. And you can see it guesses from the data what we want to see in terms of the range of the scales of the axes. I'm going to say, well, my times go from 0 to 60, so I'm going to make sure my axes go from 0 to 60. The concentrations, or the y-axis data I was provided, go from 0 to 50, so I'm going to make sure that the axis has all of those values. And then you can see each of the concentrations is plotted, and we can see this curve that is asymptoting on 0, as you would expect for a first order exponential decay.